Today we also start one important topics, which topics is related to measure theory, especially measure integration. We also discuss about measure integration, but in previous class we also talk about that means some measurable functions and how these functions will deal. So now we start about step functions. We are also familiar with these step functions in previous class. But now we'll discuss about this. We'll first start from some example of these functions. Here one if x greater than equal to 0 and 0 if x less than 0. Okay, and again we denote gx equal to 1 if x greater than equal to c and 0 if x less than c. Okay, these are the some familiar step functions. Now define the step functions in this way. Now let x be a set. Let x be a set. Okay, and then a subset of x. Okay, a subset of x, then define, then psi a defined by, then psi a defined by. How this way is defined in this way, so simply we write it psi a x equal to 1 if x belongs to a and 0 if x does not belongs to a. Okay, then we also talk about it psi a functions from x to r. Okay, defined in this way, and obviously we define this way, and we talk about these functions is step functions. Okay, now we erase this portion and going to discussion about on simple functions. Okay, we talk about simple functions, also known step functions. Now we discuss simple functions. Simple function. Then let we talk about in this way. Let E be a measurable set. E be a measurable set. Okay. Let E be a measurable set. Then let E be a measurable set. Let E be a measurable set. Then what happened? We talk about psi e to r be a step functions, be a functions. Okay, be a function. Then psi is said to be simple function. Then oh, has some problem occur, I think. Then psi a to r be a function. Okay, and is said to be a simple functions. Is said to be a simple function. It's said to be a simple function if there exists a collection, a1 a2 an a1 a2 an of real numbers of real numbers and a collection en and a collection en or I equal to 1 to n I equal to 1 to n be measurable subset of E be measurable subsets of E with union of I equal to 1 to n I equal to E. Okay, then such that psi x equal to ai for all x belongs to ei for I equal to 1 2 n. Okay, then we talk about this function. Psi is said to be simple function. Okay, now we also see in this way, if we write this one and partition into e1 e2 a3 in this way, and this one real number a1 a2 a3 in this way, then this function is defined in this way. Okay, this function is called simple function. Okay, obviously each part is going to be a real number. Okay, then we going to write in this way. Obviously, if we erase that portion and write in this way, that means some observation right here. This observation is psi x, we write a1 psi e1 x, a2 psi a2 x, dot 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 an psi en x, where x belongs to E, and psi e1 x equal to, if x belongs to e1, and psi ei x equal to 1 if x belongs to ei, and 0 if x does not belongs to ei. Okay, in this way we represent this one. Okay, now we also going to be discuss in this way. That means here psi x equal to, we represent this one, that means canonical representation of simple functions. Okay, we write in this way, this one. Canonical representation of simple functions Okay, in this way we write this one. We just write here psi x equal to summation I equal to 1 to n ai psi of eix. Okay, where x belongs to this x, and where a1 a2 dot 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 an be a collection of distinct elements of R. Be a collection of distinct elements of R, and E1, E2 En be the disjoint measurable set. Be the disjoint measurable set. Okay. Then we talk about this portions here. হ্যাঁ না আমি ভিডিও করছি Now talk about in this way. Okay, psi A be measurable if and only if A be measurable. Okay, then every simple functions be measurable if it defined in a measure space. Okay, so we now are going to definition of some integration of non-negative simple functions. What is this portion now, and going to further discussion of that. Integration of non-negative simple function. Integration of non-negative simple functions. Okay, then here we write in this way: let E be a measurable set in a measure space. Okay, let E be a measurable set in a measure space X mu. Okay, and now and let psi this E to R plus this E to R plus be a simple functions. Be a simple function. Then the canonical representation of this simple functions be this simple function being psi x equal to summation I equal to 1 to n ai psi eix. Then the integral of simple functions psi over e with respect to mu is denoted by, then the integral of simple function psi over e with respect to mu is denoted and defined by defined by integration of E psi d mu equal to a1 mu e1 a2 mu e2 plus an mu en. Okay, then we also further proceed in this way. That means just we integrate some simple functions in this way. Okay, now we obviously see about that this E psi d mu belongs to 0 infinity. Okay, now again we also let's talk about now integration of non-negative simple functions over A. Okay, that means we erase not total portion, just some portions we erase here. Okay, this one is remains same. Then we write here, that means a subset of E. If a subset of E be measurable set, then integration of A psi d mu equal to a1 mu e1. Okay, e1 intersection A plus a2 mu a intersection e2 plus an mu a intersection en. Okay, now we write in this way this observation here. Okay, this observation here, if A be measurable subset of E. Okay, if A be measurable subset of E, if A be measurable subsets of E, then what happens? If A subset of B, then integration A this d mu less than equal to V this d mu. Okay, now how this one happen also see about it. Okay, now again if we erase lower portion and going to further discussion of that, that means also write this one, if A union B psi d mu equal to A psi d mu plus B psi d mu, if A intersection B equal to phi. Okay, how this one is possible? We write in this way, AI mu of A union B intersection AI. Okay, summation I equal to 1 to n, since this one equal to I equal to 1 to n AI mu of A intersection EI plus summation I equal to 1 to n AI mu of B intersection EI. Okay, so we also write this one. Okay, this next we talk about That means we are going to some example of this. Okay, we write these definitions. Now we're going to some example and we also see this. That means which one is not Riemann integrable but is Lebesgue integrable. Okay, so it is that portions and going to some example. Too easily this one is discussed today. I think all are understand that portion. Okay, now we're going to one familiar example which are Riemann integrable but not which are not Riemann integrable but Lebesgue integrable. First we consider the function if 0 1 2 r to the power n, not here, not r to the, just r plus be defined by fx equal to 0 if x does not belongs to 0 1 intersection q and 1 if x belongs to 0 1 intersection q. Then we're going to the discussion of that. Here we write oh, there is some problem occur here. I don't know why this problem occur. Oh, why this problem occur, I don't know. Who created this problem? Who is responsible for that? Also not known. But some bastard are also create that, I think. Now we're going to be this example. Okay, just to write these functions. Now we go check Riemann integrability of f. Okay, we check Riemann integrability of f. Let p equal to x1 x2 xn be a partition of 0 1, be a partition of 0 1. Define mr equal to infimum of fx, x belongs to ir. Okay, her ir is what? Her ir is obviously some partition or some, that means interval from r minus 1 to or xr minus 1 to xr. Okay, then this one equal to what? Obviously this one equal to 0 and capital mr equal to supremum of fx where x belongs to ir equal to what? 1. Okay, now then we're going to then UPF equal to what? Okay, UPF equal to R equal to 1 to in m r delta r. Okay. This one equal to obviously 1, and LPF equal to what? Summation of r equal to 1 to n m r delta r. This one equal to 0. Then here 0 to 1 upper bar fx dx equal to infimum of UPF p equal to what? 1, and 0 to 1 lower bar fx dx equal to what? Supremum of LPF equal to 0. Then what we find? We find that if is not Riemann integral. We write here if is not Riemann integral. Okay. Now we erase that portion and going to further discussion of that Lebesgue integrality of f. Okay, we erase that portion and going to check about that Lebesgue integrability. That means Lebesgue integral of f. Okay, so how we handle it? We divide this two portion. E1 equal to I difference 0 1 intersection q, and E2 equal to 0 1 intersection q, and A1 equal to 0 and A2 equal to 1. Now we write in this way fx equal to A1 psi E1x plus A2 psi E2x. Okay, for all x belongs to 0 1. And then f is the non-negative simple functions. Then f is the non-negative simple functions. Okay, then we talk about this portions. Hence Lebesgue integral of f is given by Lebesgue integral of f is given by integration of EF d mu equal to A1 mu E1 plus A2 mu E2 equal to 0 multiplied by 1 and 1 multiplied by 0 equal to 0. Okay, so what happened? How this one happened? Since mu of E1 equal to 1 and mu of E2 equal to 0. So we talk about that, hence AB Lebesgue integral. Okay, now we also discuss one important example, which one is Lebesgue integrable or not. So today we discuss first we talk about step function, then simple functions, then canonical representation of simple functions, then obviously integration of non-negative simple functions. Then we talk about one important example, which is obviously Lebesgue integrable but not Riemann integrable. So today we stop here.